Ebrahimi, he's faculty at our department. So he's an assistant professor in the School of Electrical Engineering and Computer Science at Washington State University, where he just joined, so in August 2024. So he received his PhD degrees in electrical engineering from the University of British Columbia, UBC in Canada. And also he was a postdoctoral research and teaching fellow at UBC. He received his master and bachelor degree from Sharif University of Technology in Tehran, Iran. And he is also a registered professional engineer with Engineers and Geoscientists, British Columbia. His primary research interests include modeling and control of renewable energy systems, power electronics, and electrical machine, as well as power hardware in the loop, real-time electromagnetic transient simulations. So with that, the floor is yours.
Okay, hello everyone, and thanks for attending. As Said was saying, most of you are attending because it's mandatory, but it's not. Last week that the session was over, the previous seminar, there were some books that are left here, and I saw many of them were for electrical machine drives, and none of you touched even any of them. So I thought, why these guys aren't interested in electrical machines and electrical machine drives, because electrical machines are what move the world. So without electrical machines, nothing would move. I do agree, you just have to walk yourself. So I thought probably what I can do best for this seminar is at least try to motivate you to be a little bit more interested in the concept and topic of the area of electrical machines and controls. So today I'm going to overview what are called brushless DC motors. I guess most of you may not be in this area, so may not be deeply familiar with this. So I try to have an overview of the structure and principles of these machines, and then the control methods that are used for this type of machines, and also how we can do something more that we've done recently. So what we expect you to get from this seminar today is to learn a little bit more about the types and construction of common brushless DC or BLDC motors, and how they operate and how we model BLDC motors. Specifically, we use rotating reference frames to model BLDC motors. We look at their steady-state characteristics and how we can analyze them, and how they are similar with brushed DC motors. Why do we say brushless DC motors? And their drives, how we drive the motor, and what are the sources of electromagnetic torque ripples, and what we have done to mitigate this problem. So before I start, when we say brushless DC motors, they're not actually DC motors. They are synchronous AC motors. So this is just a set of knowledge. Now we say why they're called brushless DC then. So there are coming in different sizes and different types for many different applications. So in many of the applications, you usually look for positioning control. So these are usually used in industry for position control, and they come in different shapes and different power ranges. I'm pretty much sure that you've seen this conveyor belt when going shopping, right? So they're used in many applications if you want to have precise positioning. So the applications are also in electric vehicles, in e-bikes like this. They're used in electric vehicles and e-bikes. They're also used for propulsion. For example, in drones, they use BLDC motors. So they have tons of applications. I've just listed a few here. So they are used in appliances. This is a picture of a washing machine, the back of a washing machine if you just open it up. They're used in power tools. For example, it's a drill. It's a cutaway of a drill. So they're used in elevators. They are used in pumps. Here you can have this BLDC motor that just is powered by solar, and then it pumps water underground. So they are used as robots. They're used in robots for many industrial automation. They're even used in computers. So you have You may remember those floppy disks in computers, in disk drives, in fans of computers, in many peripherals in computers. So they have tons of applications from very small power to high power. So, for example, this is the picture of the ceiling fan here that use BLDC motors. So they're even used in toys. So here is a BLDC motor that drives the machine. So, but the list does not really end here. So if you just want to see what are the applications of BLDC motors, just Google it. There are tons of applications. The BLDC motors are used. They can be as small as the tip of your finger or as big as several kilowatts of power. So don't miss on this. There are lots of applications that BLDC motors are used in, and it's good to have a knowledge of BLDC motors and their applications. Okay, so just to know, the typical configuration of BLDC motors are like this. So
yeah, you just continue. I'm just playing around.
Yeah, so similar to many of other electrical machines, so we have a stator system. So this is the stator of the BLDC machine. So we have a rotor, so you're familiar with this. So we have a stator that is stationary. We have a rotor, that this rotor goes inside the stator like this. These are end caps for the housing. And we also usually have some power electronic converters in these types of machines. And we'll see why, because they are driven by power electronic converters. So you see that this is a stator with some windings wound here, the rotor, and there are some power electronic converters here like this. And this is the rotor that goes inside this. Let me ask you a question. Do you know how many poles this rotor has? It has 8 poles, yes. N, S, N, S, N, S. So these are the magnets that are glued to the stator. So the rotor is usually made of permanent magnet. So what we usually have is a round rotor like this. And what we do is to glue permanent magnets on top of the rotor. These are called surface-mounted PM rotors, or SPM rotors. You can have different other types, but usually surface-mounted rotors are used. So for example, this is a rotor that has 2 poles, 2 pieces of magnet here, N and S poles. This is a 4-pole machine. So N, S, N, S. This is 8-pole machine. So these rotors go inside the stator like this. So this is the rotor that goes inside the stator. So the stator on the other side looks something like this. So you can have a stator like this. This is the top view and side view. So you see that you can have some windings wound on the stator, the slots of the stator. So these are called concentrated windings. So you can have concentrated windings wound here, and you can connect them to different phases. So, for example, if you have 3 phases, you can assign that, okay, I'll assign number 1 and number 4 and number 7 and number 10 to phase A, then 4 other to phase B and 4 other to phase C. And then depending how many poles you want to have this machine have, you can wind them differently. You can make the flux to flow like this and make it 4-pole or make it 8-pole, depending how you wind the windings. So you can also have what we call distributed winding. I'm pretty much sure that you're partly familiar with this from your machine course, how we wind a stator winding sinusoidally. So depending on the application and how much you want to pay for it, so basically they come in different configurations, but these are very easy to configure. So this is also the rotor, the permanent magnet rotor that goes in. So these are called the conventional in-runner motors. So the in-runner is that you have a stator and the rotor goes in. So you also have what are called outrunner motors. So in outrunner motors, it's the opposite. So you have the stator and a stator winding, and rotor is the one that is outside. So the one that rotates is the outside one. So here These are the stator windings, and the rotor is outside, and it has some permanent magnets glued on top of it. So this is the one that rotates outside, like a fancy. So you can also have what are called in-wheel outrunners. So you can also now use this technology and put them in wheels. And you tell me what would be the application, right? So, for example, here we have the stator, and then rotor is the one that is outside like this. This is the rotor. And then it goes inside the wheel, and then it's used for EVs or e-bikes. And you also see that we have some power electronic board here, because we need the power electronic board to drive the machine. So BLDC motors can be driven. So this is the structure. So we also need to drive these power electronic converters. So typically, again, as I said, BLDC motors are actually asynchronous AC motors. And the reason that we call them brushless DC motors is that they try to resemble the characteristics of DC machines, conventional DC machines, but without any brushes. You know that the brushes in conventional brush DC motors are their pitfall. They cause mechanical wear and they need a lot of maintenance. So this is brushless, and they're also fit from DC power. But they are synchronous AC machines, permanent magnet synchronous AC machines. So what you have is a permanent magnet synchronous machine like this, that we can put the symbol here, the 3 windings of the 3-phase permanent magnet, and it is driven by a 3-phase inverter. And the inverter is fed from a DC power supply. So you can have a configuration like this. So for this, you need to have a DC power supply. So this is, for example, the machine, and it comes with a pack of inverters and supplies to drive the machine. Or what you can have is everything packed together, and you can also drive it from AC power source. So in this case, everything comes together. You can connect to AC power supply. So it is internally connected to a rectifier. So the rectifier, you know how it works. It's a thyristor-based, so it can be diode-based. And then you get a DC voltage here, you filter it out, and you will have a DC voltage. It is also connected to inverter, and it drives the machine, right? So they come in different packages and for different purposes. But let me ask you a question. How can you control the speed of a synchronous machine? So let me formulate my question like this. So I have a synchronous machine, and then it's not spinning, of course. I put it on the desk, and then I connect it to outlet of the power outlet here. So it's 60 hertz, right? Do you expect it to move or not? Yes, no, why? If it was an induction machine, did you expect it to move? Of course, yes. But what if it's synchronous machine?
Something else needs to spin it first, and then it'll synchronize, and then it'll run on the wall power.
That's exactly the reason. So you have an MMF of a stator that is connected to the outlet, so it rotates with 60 hertz, a speed that corresponds to 60 hertz. But MMF of rotor of the synchronous machine does not move. It's still stationary. You need some mechanism to spin this up so that the output voltage generated by the machine also matches the 60 hertz, then you can synchronize. So then what if you want to control the speed over a wide range? So you need to have a power supply that allows you to control the frequency over a wide range, right? From very low speed to start up and then slowly increase it. So that's why we need a power electronic converter. Basically, what it produces here is a couple of voltages that you can adjust the frequency. So to know that, you need to know a knowledge of the speed of the machine then, right? And also the position of the rotor. So because of that, you will need some sensors here to measure this rotor position, and from that it calculates the speed of the machine, and then from there it calculates how those switches should turn on and off so that it produces a suitable voltage. right? So you need to have some sensors here. So we usually use what are called Hall sensors for BLDC machines. So Hall sensors give you an idea of the position of the rotor. So from there, you can calculate the speed, etc. So the way the Hall sensors operate, let me briefly say what Hall sensor is. It's not scary. So you have what is called the Hall element. So if you have this Hall element here and you connect it to a power source, so there would be some electric charge moving around here, right? So now if I impose this Hall element in a magnetic field like this that I have shown here downward, so you know that the electric charges will be pushed or pulled by magnetic field, right? Lorentz force, right? So then depending on whether this magnetic field is this way or that way, those positive or negative charges will either just go to this side of the Hall element and negatives here, or positives here, negatives here. So based on that, the voltage that you get from this side of the Hall element will be either positive or negative. So you can have a logic that if I get a positive voltage, it means that magnetic field was this. If it's negative, it means that magnetic was in the other direction, right? So based on this, then it gives you an idea of the magnetic field. And we also know that there are magnets mounted on the rotor of the BLDC, right? Then if I try to find out what is my N pole or S pole now at this position, then I will have an idea of, am I under S pole or am I under N pole, based on the signal coming from the Hall sensor, right? So then what we do is we put three Hall sensors here that try to basically detect whether you're under N pole or S pole of the rotor, the magnets that are mounted on the rotor. But we don't usually put the Hall sensors inside the machine because we just want the signals to interact with the magnetic field from the poles, the magnets of the rotor. We also know that there are magnetic field inside because of the current flow in the stator winding. So because of that, we take the Hall sensors out. So somehow now we have to replicate that magnetic field that are on the rotor so that these Hall sensors can detect. So what they do is, we put some magnetic tablets here, some tablets of magnet, that are very much similar, that resemble the magnets that are mounted on the rotor itself. But we take them out. So we glue them here, very similar to the magnets that are on the rotor, with the same number of poles, etc. Now that this, so we take everything out. Now that this shaft rotates, Hall sensors detect the N and S poles of the magnetic tablets here, which gives us an idea of what is now the N or S pole of the rotor inside. So there are some advantages and tricks that we can do with this, because you can now shift and adjust those magnetic tablets intentionally so that you provide some phase shift, or if you have some misalignment of gluing these magnets, then you will be in trouble and you will have some torque ripples. So that's how then we can get an idea of the speed and position of the rotor from Hall signals. So then what we have here is a DC power supply that can be from another stage of AC power supply, doesn't matter. You have a DC power supply that is driving 6 switches. So it is connected to 6 switches, and these switches are driven by a logic. And the 3 terminals, output terminals of the inverter, are connected to the stator winding of the machine. And this is just a schematic. And then we have 3 Hall sensors that try to detect the position of the rotor and speed of the rotor. And then we also have a rotor here. And then when it rotates, then N and S poles of the rotor will give different signals to Hall sensor. But that's basically pretty much the structure. So we also need to model this for the purpose of simulation, implementing new control methods. So similar to other types of electrical machines, so what you need to do, so let's assume here that we have our stator, we have 3-phase AS winding. AS, you know that this is going to be the magnetic axis of phase A. BS axis is going to be like this, and C axis is going to be like this. So these are the magnetic axis of the stator. We also have a rotor like this that has N and S poles. For simplicity, only 2 poles. And then we also have 3 Hall sensors mounted here on the stator to detect the position of the rotor. So to model this, basically what you need to do is to write the voltage and flux equations for the machine. So the voltage equations for the windings are resistive voltage drops on each winding. So we have 3 windings for a stator, AS, ES, and CS. So resistive voltage plus Faraday's law, the rate of change of flux, right? Same for BS or in vector form like this. So now there are different ways that you can model this machine with different complexity and detail, higher level of detail. So you can assume that if I open circuit the windings, so if I open circuit the windings and I rotate the shaft, because there are magnets on the rotor, you will have voltages induced at the stator terminals, right? These are called back EMF voltages or open circuit voltages that you get. So if you rotate the shaft, they can be either like the sinusoidal 3-phase voltages induced. They can be like this, what we call quasi-trapezoidal or pure trapezoidal. So they range, basically, if you buy different machines, they come in different ranges. I've seen a lot of machines like this or like this, like this. So it all depends on the structure and how they're manufactured. So you can now assume that they're sinusoidal for simplicity. But even if they're not, if they're like this or like this, you know that how you can reconstruct these waveforms by adding different harmonics, right, to the equation. So I can represent this waveform like a sinusoidal waveform plus different, a 3rd harmonic, 5th harmonic, 7th harmonic, etc. So then the voltage equations are like that, and these are also the flux equations. The flux equations, I'm pretty much sure that you're pretty familiar, but it's like this. Flux is inductance multiplied by the current, right? So we need to find the inductances of different phases. For example, we have self-inductance and mutual inductance. For self-inductance, it's like this, leakage inductance plus magnetizing inductance. Mutual inductance between phase A and B or B and C, they can be driven like this. So it's not scary, you can quickly find out how they have drive. So for example, between phase A and B, mutual inductance is, if I energize phase B, how much flux will contribute to phase A? So if I energize phase B, I will provide a flux in this, produce a flux in this direction. So if I want to know how much of it is going to contribute to phase A, I need to project it on phase A axis, right? So if I project it down here on phase A axis, here is 60 degrees. It's going to be cosine of 60 degree, 0.5, but it's in the opposite direction. So 0.5 with a minus sign. So that's where it comes from. You can do this for different phases, and you see that the mutual inductances are like this. So we also have magnets on the rotor. So the magnets on the rotor, when this guy rotates here, if I assume that theta starts from here, if theta is equal to 0, this magnet, the flux of this magnet on the rotor shows downward here. So there would be no contribution to phase A. But if I rotate this shaft 90 degrees, that's going to be the direction of the flux. So it's going to be maximum contribution. So if you follow, you'll see that for phase A, it's lambda multiplied by sine of theta r. And for the other phases, with 100 plus or minus 20 degrees. So then these are also the flux equations. To complete, you also need to calculate to formulate the electromagnetic torque. So the electromagnetic torque from your machine course, I know that you know, is number of poles divided by 2, partial derivative of co-energy with respect to theta, right? So the co-energy, the formula is like this, but you don't need to worry, because if you take the partial derivative of the first term, it's not a function of theta, so it's going to be 0. You will only have the second term. So you just need to, because it's a function of theta, it's going to be IA multiplied by lambda multiplied by partial derivative of this, which is going to be cosine of theta. So IB multiplied by lambda multiplied by derivative of this, which is going to be cosine of this minus 102. So this is also the way we modeled electromagnetic torque. Again, if you want to include those other shapes of flux, you can include more flux terms here for permanent magnet, third harmonic, fifth harmonic. So, but you see that there are variable terms, cosine of 120 degree plus, so it's not easy to work with them like this. Because of this, we usually formulate them in what we call rotating reference frame or QD reference frame. I'm pretty much sure that you're familiar. So if we have three phases here, the stationary phases, a stationary axis, AS and BS axis, these are stationary, they do not move. So we have what are called rotating reference frame, Q axis and D axis, and they rotate with the speed of the rotor. So the way we do the transformations is that if I multiplied ABC variables with a transformation matrix, which looks like this, everything that I have in ABC coordinates will be shifted and moved to QD coordinates. So in the QD coordinates, all the AC variables become DC because that frame also rotates with the same speed. So the projection will be always a constant. So if you want to move them back from QD after you're done with your calculations, you just multiply it by inverse of the transformation. So if you apply those transformations to the equations that we have here, so you will get these equations in QD coordinates. So let me ask you, are these variables AC or DC? ABC variables. These are AC variables. Not only AC variables, but also with varying frequency because the speed of the shaft is not constant. But when you move them to QD coordinates, they all become constant DC, at least in a steady state, right? So what happens is resistive voltage drops plus the rate of change of flux plus omega multiplied by lambda, which is defined here. So these are called the speed voltage terms, right? So with this, then you can also transform the equations of the flux from ABC to QD coordinates. So if you do that, what happens is this matrix of inductance, simply if we have lambda A, lambda B, and lambda C for three phases, I'll have lambda Q and lambda D, and they become like LS, which is defined as function of this, multiplied by IQ. It's going to be very simple, very elegant. And if I transform this second term into QD, it just becomes lambda M, only on the D axis, because that's how I define my QD axis. So the equations become really simple. So if I want to summarize, these are going to be the voltage equations if I want to model the machine, and everything is going to be DC in a steady state. These are going to be flux equations, very easy. And I also need to somehow modify the equation of the torque. If you look at this term that is in here, IA cosine of theta plus IB, you'll see that this is actually 3 divided by 2 multiplied by IQ, if you apply this transformation as well. It's going to be very simple. So the way we model the machine is like these simple equations you just quickly implement in MATLAB or any software. And then there's flux equations and a torque equation that is very elegant and simple like this, right? We also see here that the torque of the electromagnetic torque is only dependent on IQ, not on ID. This is something to note here. So then if we want to take a look at the analysis, the characteristic of this in a steady state, let's say. So in a steady state, let's say that we have applied 3-phase voltages to the machine like this. So a square root of 2 RMS of voltage cosine of these angles plus a delay that we call advanced firing angle, phi v. So we have applied these voltages to the stator of the machine. So what happens is that if I move them to QD rotating reference frame, they'll become like this, right? It's going to be square root of 2 V RMS. It's the peak of the voltages, phase voltages multiplied by cosine of phi v. So now these are going to be the inputs to my QD model. And I know that in my equations in QD, if I'm in a steady state, because everything is DC now, D over dt terms will be equal to 0, because everything is DC now. So it's going to be VQ equals RIQ plus omega R lambda D. Lambda D is also LDID plus lambda. VD is RID minus omega R LIQ, right? So they look like this. Now you can solve for ID from the second equation here based on VD and IQ and plug that ID in the first equation. And then you'll get this torque equation because we know that torque is 3P number of poles divided by 4, the strength of the permanent magnet and the rotor multiplied by IQ. I'm using capital letters because everything is a steady state. So you'll have this expression for torque.
That is for steady state, right?
In a steady state.
But otherwise,
you have actual IQ, not the IQ in a steady state.
Okay.
Right? So in this case, what happens if I set phi equal to 0? This is called the common operating mode, where phi is equal to 0. So in this case, V key is going to be equal to peak of the voltage. VD is going to be equal to 0, like this, right? So the equation will be simplified because the second term disappears, right? It becomes like this. So let's have this, and let's see how it is analogous to conventional brushed DC machines. So we have this equation also for VQ. And I remember that and I'm sure that you remember the equation of the brushed DC motor. Remember we had the armature. There was a resistance of the armature, at least in a steady state inductances. And then we were showing these squares and then a circle. Remember that? For back EMF. So VA armature voltage was resistance multiplied by I armature plus omega RKB. So this is also the equation for the voltage of the brushless DC machine. So if we formulate the back EMF of the brushless DC machine is omega R multiplied by lambda is omega R multiplied by kV, almost analogous. So electromagnetic torque is 3P divided by 4 lambda, and IQ is a constant multiplied by IA. So very analogous to brushed DC machines. Torque has a torque speed characteristic is like this, the relation between torque and omega. For brushed DC, it was like this, kV VA minus omega. So this you can say that this is a constant, a voltage minus omega R kV. And here the input was VA, the armature voltage. Here the input is VQ that we have here. But VQ is also a function of VDC. So we both have VDC inputs, and everything, all the equations look very similar. So if we look at the characteristic of a permanent magnet, brushed DC machine is dashed line, and brushless is this solid line. So very similar to brushed DC machine. That's why they are called brushless DC machines. They're actually AC PM synchronous machines that are driven by converters, but because they resemble the characteristic of brushed DC machines, they're called brushless DC machines. So we also need to drive the converter. So to drive the converter, you need to operate these 6 switches that are here. So we usually have very two commonly used algorithms. One of them is called 180-degree operation. The other one is 120 operation. So basically, you need to formulate the voltages at these nodes with respect to the negative rail, and then relate it to the switching signals. So we have 6 switches and 6 switching signals. So we have a table. That table is based on the position of the rotor. So if rotor changes, you will just have this hookup table, and then you turn on and off other switches. So the reason they are called 180-degree is that each of the switches here will be turned on 180-degree and turned off 180-degree. So these are the switching signals. So upper and lower switches here will be switch complementary, either on, off, on, off, on, off. And with that, these are going to be typical voltages of the phase voltages. And these are going to be typical line or phase currents. So you see here that this is phase A. I can also move everything to QD, and these are going to be the QD currents, IQ and ID like this. We know that the harmonics that are on top of this waveform, so you can assume that this is a fundamental frequency component plus some harmonics. those harmonics will be the ones that are ripples here. The fundamental components of these waveforms will be the average part. The harmonics will be the ripples. You also remember that torque was related to IQ, the constant multiplied by IQ. So you can expect that the electromagnetic torque is just a scaled version of IQ. So if you have ripples in IQ, you'll also have ripples in torque. So this is going to be a little bit of problem because, not a little bit, it's going to be a problem because if you want to have precise positioning, you need to have low torque ripple, right? Otherwise, you'll have a lot of vibrations. So 120 degree, in 120 degree operation, the switches are switched like this with another table of logic. So in this one, every switch is on 120 degree. So those two switches on, and the upper and lower switches, each of them are on for 120 degree. So they should also be off for 120 degree. Both, so one leg will be off and floating in 120 degree. So it's a little bit complicated, but the typical waveforms look like this for the phase voltage and for the current that looks like rectangular waveform like this. But these are the typical waveform. Again, these have lots of harmonics, and harmonics means torque ripples. So then basically, you can also apply PWM on top of these switching signals. So 120 degree, each transistor is on for 120 degree. Of course, because of that, they're not operating complementary. And for 120 degree, both of the switches are off and that leg is not connected to VDC. So we are not using the DC voltage that we have completely. We are not utilizing it. But for 180 degree, so it's on, off. So either of them is connected to, at least one of them is connected to the DC terminal. So we have higher DC voltage utilization. But the thing is, both of them have high torque ripples. So here we'll focus on 180 degree commutation and what we have proposed here to mitigate the torque ripple in this. I needed to have this introductory so that you know what we have done here. So if we have this, we know that, let's say that there is no PWM here. If there is no PWM here, so these are the two switches here. These are the gates of the two switches here, and these are the two gates of the two switches for phase C. If we don't have any PWM, and if you follow the signals here, you'll see that there would be, at any moment, there would be one transistor, one leg, one phase, that is solely connected to either positive rail and the other two are connected to negative, or the other way. One is connected to negative and the other are connected to positive. So with this, we give names that the one that is solely connected, we give it Vx, we call it X. So, and you can formulate it, and that one is going to be 2 multiplied by VDC divided by 3, based on the table that we had. And the two others that are connected either to negative or to positive, we call them Vy, and they're equal to minus VDC over 3. Know that the sum of them should be equal to 0. So VB plus VC plus VA should be equal to 0, or any combination. So in our proposed method, we apply PWM only to one of the switches. For example, the one that is at the top, or the one at the, you can also do the one at the bottom, but we only apply PWM to the one at the top. So when the PWM is on, so you'll have either 2 VDC divided by 3, 2 minus VDC, or the other way, or any of the combination of the phases. But if the PWM is off, what happens is, if you turn this guy off, the current that was flowing here will flow through this parallel diode at the lower switch. So all of them will be connected to the negative rail. So the voltage will be equal to 0. So for all the phases. So because of that, we can formulate the voltages like this. We define a variable S that can be -1, +1, or 0. If PWM is on, we also give these intervals the name, interval 1, 2, 3, 4, 5, 6. So if we are in interval 1, 3, 4, S should be equal to -1. When we are in even intervals, S equal to 1. And when PWM is off, S is equal to 0. And then we provide a general formula like this, that the voltages of the stator windings can be formulated like this. And then based on these formulas, we can find the rate of change of the current in all the three phases. And we formulate them based on VDC, R, and back EMFs. So we formulate the derivatives of the current, and we also have this equation for the torque. So if we plug in these equations and do extensive mathematical manipulations, you can formulate the electromagnetic torque like this, the derivative of the electromagnetic torque, like this box. So what happens is, if you analyze in every sector, analyze this equation in every sector, you'll see that this term is always not only positive, but also always greater than this second term. This third term is also, because it's multiplied by resistance, is small, you can ignore it. So then whenever S is equal to plus or minus 1, it means that 1 PWM is on. So this term will be equal to a positive number, right? So dt over d torque over dt, if PWM is on, it means that S is plus or minus 1. It's going to be greater than 0. If S is 0, it means that the PWM is off, here and here, then it's going to be 0. You'll have only this term and it's negative. So what does it mean? It means that the rate of change of the torque when you have PWM on is positive. It means the torque is increasing. And when PWM is off, rate of change of torque is negative. It means that it's decreasing. So we can use this to mitigate the torque ripples. So if you have this PWM signal and compare it with a carrier wave, so you'll see that when PWM is on like this and the voltage is connected to 2 VDC divided by 3, torque is increasing like this. And when PWM goes off, torque decreases with the slope F2. We define F1 and F2. So what we have proposed here, that we formulated these partial derivatives for the torque. And what we do here is, to minimize the torque ripple, we try to make sure that if you have a reference for the torque, at each PWM switching interval, which is very fast, the end point matches the torque reference that you have. So we formulate everything so that the torque at the end point here of the PWM becomes equal to the reference value that you were looking for. So if I want to try to relate torque at the beginning of the switching interval and at the end of it, and these two torque value, the slopes, you can say that the amount that this has increased, T at K plus 1 minus T at K, moments of switching, it is equal to the duty cycle of the converter multiplied by this length, multiplied by F1, plus how much it comes down with F2 negative. You can add them like this. This is the amount that it increases, this is the amount that it decreases. If you add them, that's going to be the amount that it. So if you want this torque at the end to be equal to reference, you just replace it with TF, and you derive this equation, the duty cycle at each switching interval. So we formulate the duty cycle based on the reference of the torque at the previous value, and also the slope of this that we calculate mathematically, and then the switching frequency or switching period. So then at every switching interval, we can dynamically adjust the duty cycle so that you make sure that the torque at the end of the switching interval matches the reference value. So then this is the way that we have implemented. We have that inverter connected to brushless DC motor. You have some Hall sensors that detect the position. They do estimation of angle and speed. And if you have angle and speed, you can estimate the back EMFs. If you have the back EMFs and you measure the currents, you can estimate the torque. So if you apply these values and the duty cycle that you calculate to that formula, you can calculate the duty cycle of those switches at every switching interval. and you can feed it to your inverter. So this is the experimental setup that we had there. And so this is a BLDC motor, for example, a 48-volt BLDC motor. So the setup is here, DSP connected to the machine, drives the synchronous machine, which is a BLDC machine. Shaft is connected to another DC machine, brushed DC machine that looks like a mechanical load, a dynamometer. It's also driving a load here. You can adjust the load, data acquisition system, oscilloscopes. So this is what we get from this method. So these are experimental results. So with conventional 180-degree commutation, the reason we chose this one is because it has high voltage utilization. So if we do not change, if we also apply PWM switching, but do not change the duty ratio dynamically, I think it was 60%. So you get this waveform for the current, phase current, and this is going to be the profile of the torque. You see that there are lots of ripples. The average is 0.6 Newton meters. The speed is almost 1,000 RPM, but you have a lot of torque ripple. So if you apply our proposed method and you try to dynamically adjust the duty cycle within every switching interval, what happens is that you can see that we have not changed the profile of the current much, but you look at the torque ripple, the ripple here is around 0.42 Newton meters. We have been able to decrease the torque to 0.09 Newton meters. So because we change the duty cycle dynamically like this, instead of having a fixed value, like the third one. So we also tested this under transient conditions to see if it adjusts fast or not. So for example, here we change the reference value of the torque, the mechanical torque, from 0.3 Newton meter to 0.75, and we see that it tries to track the reference torque very quickly because it just tried to brute force, try to adjust the duty cycle, and there is no control loop, PI, etc. by adjusting the duty cycle dynamically. So it is very interesting. This area is interesting. That's why I just wanted to make you motivated. So I just have to say that we did this work at UBC before I come here a couple of months ago. And this was presented at the conference and it got the Outstanding Paper Award. So this is really a hot topic. So brushless DC motors. So my colleagues at UBC, Ziliang or Bruce, Rahul, and myself, and another professor, Professor Yaskevich, was my PhD supervisor. So this is pretty much all I wanted to discuss about. So an overview of the operation and characteristics and the structure of BLDC machines, their applications, how we can model brushless DC machines, how we can do the control and drive, and what can be done, what are some challenges. This torque ripple is one of the challenges. The control is very simple, but there is no free lunch. Because it's simple, it also have high torque ripple. But this is what we could do for mitigating those torque ripples. Okay, thank you so much.
Thank you. That was very interesting and engaging presentation.
Do you like to work on electrical machines now?
Yeah.
Give it a try.
These guys are more efficient than you think. Just go to easiest thing that they can do. So let's go by people online and see that if anybody has any question. No?
Let me put some pictures like this that you get motivated.
I had a quick question. Maybe everyone else already knows, but what exactly is a torque ripple? I can kind of like qualitatively guess, but I might have missed in the presentation.
Yeah. So what we expect for the torque, so you expect if you have a torque to be say 0.6 Newton meters, constant. But what you have here is a constant with some of ups and downs on top of it. So these ups and downs are called ripple. It means that you want to apply some force to rotate the shaft, but it loses and then makes it harder. So instead of rotating like this, it rotates like this. It tries to push it faster, then release it, push it faster, release it, instead of applying a constant 0.6 Newton meters, it tries to, and it causes vibration. So these humps and sinusoidal on top of a DC variable are called ripples.
And so the vibrations are what we want to avoid.
This causes vibration because those torque ripples cause vibration. These are not desirable because you want to operate in precise positioning control. So I want to, for example, rotate it like this, and then it goes like this. So, but that's not what I'm looking for position control, right? So I want to go as smoothly as possible, so without much ripple. So otherwise it's going to be like this. So if you try to, and if torque is high, so you go like this. So torque ripple also causes a speed ripple. The torque and speed are dependent. We look at those characteristics. So if the speed also has ripples, it causes noise. Instead of having a smooth operation, if you've heard that, now it's because of the ripples in the speed. It also causes mechanical wear and tear. So you try to minimize torque ripples. There are other methods that have been used in the literature to try to achieve and address this. For example, instead of applying 120 degree or 180 degree, they apply 150 degree and somehow make things better, or they try to formulate things differently and try to basically distinguish between the sources of torque ripple. One of the sources of torque ripple is that misalignment of those magnetic tablets that I said. So that's one of the reasons that we apply some methods. We filter the signals coming from the Hall sensors somehow to minimize torque ripple coming from them. Or one of the reasons is that that back EMF that I showed and we assume that is sinusoidal is not actually sinusoidal. So it has those quasi-trapezoidal. They also contribute to torque ripple because it's like some harmonics multiplied by some currents that you do the math, you'll see that it will cause some other ripples. So the other one is what we call commutation torque. Commutation is between when a phase goes out and the other phase comes in, it's called commutation. And because of that, there would be some torque ripples. And they try to basically formulate that commutation and see how they can fix it. So there are lots of things going on in this area.
You said it is optimally reducing the ripple. So
Not optimally.
not optimally.
There is no, we haven't done any optimization yet. I said brute force.
Brute force. So because you did formulate the ODE for your torque, right?
So that's the concept. So we know that we have some ups and downs in torque. So we try to make this one to always be on top of the reference. So if everything was perfect, because this is very fast, we should have a constant line, right? But we cannot do it because it uses the value of torque from the previous value and we have to calculate it. So we need to have some estimation. We need to estimate the back EMFs that are used in the equations for F1 and F2. Because it's not perfect, so you still see some torque ripples like this. If everything was perfect, then you should have seen, because it's very fast, in the order of several kilohertz, then at every, let's say, microseconds, you try to match it, then you should see a constant line, but it's not what happens in reality, because you need to have some predictions.
Right, but you did derive the torque expression, like the derivative of the torque. Wouldn't you have gone, or why is the reason not going the linear controls way, like formulating a frequency model or transfer function and then trying to fit a PI controller for this because you have the derivative of your torque?
Yeah, you don't need any PI controller here because you can, but you don't need it here because you can say that it makes things simpler when you want to load everything into your microcontroller. Mm-hmm. For example, you can have other types of control, space vector modulation. So they have internal loops of current control and then higher level controls. But here it's very simple and easy and straightforward to implement. It says that I calculate the torque and I want it to be equal to my reference at every next switching one.
So was there like, I'm just wondering, is it as good as a PI controller would have been, or it is better?
We haven't done that here to
Okay.
compare it with space vector modulation. We actually did it partly, but it's not that fair to compare because that uses high frequency switching. But the switching that we have here is much lower. Maybe I can show you. You can check the paper. I can also show it here. We have compared it with the space vector modulation with those PI controllers. They're in the paper.
Okay.
But we've shown that the torque ripple is a little bit small, but smaller than the conventional space vector modulation that uses PI. But it can be done. The comparison is not that fair. We have to also analyze the losses and the torque ripple, things like that, to say that yes, ours is better. So what we've shown is that it was really better. It was able to achieve lower switching, lower torque ripple, little bit lower. But just to have a bold claim, it has to be tested and verified. But you can check the paper. We have comparison between space vector modulation with PI control and also this method. And we've shown that because the switching frequency here, we only switch upper leg transistors. A space vector modulation switches all of them, right? So we've shown that the frequency here, the effective frequency, can be 4 times higher if you want to have the same number of switchings. So in that analysis, we assume that, okay, now, for example, the space vector modulation should operate with 5 kilohertz. Here, to have the same number of switching, for fairness, we can operate with 20 kilohertz. So we did the comparison, and ours was able to have lower torque ripple. But the reason I'm saying it may not be fair is that when you have higher switching frequency, you also need to consider for switching losses. So what if you have higher switching losses? So that's why I'm saying that to make a bold claim, we have to investigate more. But this is by itself, it's so far shown that it's very promising, and we have extended this and we have submitted to the journal. Got the best paper award.
Thank you.
Thanks.
Thank you for the great presentation, Professor Milad. I really, I really found the whole tutorial and motivation you set up for, and finally ending with your actual work, very helpful for my own understanding. So I kind of have questions on 2 fronts. One is regarding the ripple itself, and one regarding the actual the procedure you are doing regarding changing duty cycle. So let's talk about the procedure first. So duty cycle itself is something which I understand is makes sense when an output and an input regarding the firings of the thyristor. It makes sense in a specific time period, right? And you are so you are saying that we change the duty cycle at to kind of track an output reference torque. So how exactly does that work? I'm in my mind, I'm just understanding from regular power electronics, some steady state to achieve that. Okay, I get it. Yeah.
So this is what we've shown here is one switching period. So if it's 20 kilohertz, the switching frequency is 20 kilohertz. This is not what you see here. Let me go back. So this is not this period. That one is just one period here.
Yeah.
So this is, we've shown just to show, if it's in the order of 20 kilohertz, this is very small in the order of microseconds, millisecond. So that period that we're showing here is just very small period here. That is called switching period, right? So in switching period, you have a carrier waveform that operates, let's say, with 20 kilohertz, and you compare it with a duty cycle. This duty cycle in the next switching signal can go a little bit higher. In the next switching, it can come lower, go higher, lower. So what we do is that we adjust this duty cycle, we shift it up and down. At the beginning of the interval for the next interval. That's one of the reasons that it's not perfect also, right? So what happens is this one is fixed. It's coming from controller. There's providing a carrier of 20 kilohertz. This one is your input. You can adjust it at every, let's say, 5 microsecond, right? So if you try to adjust this one, you can also put it in the equations, and how you adjust it, you adjust this based on this equation. So at the beginning of every switching interval, you calculate this, you adjust it for the next one, you make it higher or lower. So what happens is, so this is higher than the carrier, it turns on that phase, it connects that phase A, let's say here, to DC terminal, and then it disconnects because it's going to be off, and then basically it becomes off and the current goes from the lower diode. And then it also makes it on like this. So this is done at every switching interval. It's a high switching frequency interval. So this is about how we do this. And of course, this is done with my DSP to have this high speed. And the other part was about the torque ripple.
Continuing on this. So just as someone who does not know how practical changing duty cycle so frequently is, does it cause any sort of changing the firing duty cycles? Does it cause any sort of wear and tear, or is it like a free lunch? We can change it.
We can just change it
infinitely. Awesome.
Because what matters in terms of wear and loss. So what matters is so for the switch, it doesn't matter if you turn it off here or if you turn it off in the middle. So if I make the duty cycle higher, it means that this orange line has come here, and this one, instead of turning off here, it turns off somewhere in the middle here. Right? So what happens is at the end of the day, in one switching period, you have one on-off. So that's what causes losses. Doesn't matter where to make it on and off.
Yeah.
So duty cycle doesn't matter as much as I know, maybe.
Yeah.
But what matters is the switching frequency.
Thank you so much.
You do it by your controller. Controller gets some inputs, gets the value of speed that go into the equations here, switching frequency, calculations of the torque, and then controller calculates this. In the controller DSP, it generates basically duty cycle and switching signals for the next switching interval.
Thank you so much. And regarding that, the source in the torque ripple is the ripple in the current, and the cause for the current ripple, the primary cause is the imperfect sinusoidal created by our switching circuit, or is it something else?
Let me explain it based on this. So this is the model of the machine. Basically, this is the model. So you have a back EMF here. So some voltages that I showed you, it can be pure sinusoidal, trapezoidal, quasi-trapezoidal. Inductance, resistance, and whatever voltage is connected, it determines what would be the current, right? So what would be the sources of the current? You have one voltage source connected here, one here for the three phases. You have RL, and you have another voltage source. So do the math. So two voltage sources divided by R and L. So it's going to be this one minus this one divided by this one, divided by the impedance, right? So if you have higher harmonics here, you can expect to have higher. Let's say that these are pure sinusoidal. If you have higher harmonics here, you can expect that those harmonics should flow. If you do superposition, let's say that these are pure sinusoidal, you do once for the fundamental component and superposition once for the harmonics. For the harmonics, these are going to be equal to zero, superposition, right? It's going to be those harmonic voltages divided by this impedance. So if you have higher harmonics here, you'll have higher harmonics in the voltage, you'll have higher harmonic in the current.
Sorry, I missed that. So you mean to say when the source itself has harmonics, that's the reason, or is it even if you use EA, EB, EC, these, can I assume they are sinusoidal themselves?
You cannot assume.
Okay.
For modeling, you can say that they're sinusoidal, okay. But the way, so here when we wanted to formulate, we said that if they are sinusoidal, but in reality, they're not sinusoidal, they look like this. This is the actual voltage of phase A.
Yeah.
So you can say that this is a sinusoidal waveform.
Yeah.
and the amplitude is 2 divided by pi multiplied by BDC, something like this, if I'm not wrong, plus some harmonics.
Yeah,
Third harmonic.
so this is because of the circuit, like because of
this is because of the logic of the switching.
Yeah.
So that's one of the reasons. The other one is because of this. This is when a phase turns off. So you see that this is the phase of the current of phase B. So you see that phase B is 0. The current is 0. What has happened is, at this point, phase B goes out of the circuit, it replaces with another one, with another phase, and it becomes 0 and it turns on here. So these causes these notches in the voltage waveform. For example, here, this is where 2 other phases we're trying to switch. Right, that causes this notch. So these imperfections in the waveform are harmonics, and these harmonics and imperfections cause harmonics of the current. So what are the causes of these imperfections? One of them is because of these commutations that happen. The other reason of this imperfection is because of the complete nature of your switching logic that generates waveforms like this. These are called 6-step. 1 step, 2, 3, 4, 5, 6. Because of the nature of the voltage that you generate. The other cause of this imperfection is even if you were able to produce completely sinusoidal, which is not the case here, even if you say that you have been able to use space vector modulation, purely sinusoidal voltage is just very high switching frequency, which will be attenuated by the inductance of the winding, right? Purely sinusoidal currents. So what happens is that if you have a back EMF like this, you have 3 voltages connected to the stator winding, let's say pure sinusoidal, then impedance RL, then plus these back EMFs. So these back EMFs have harmonics in this case, so they will also cause ripples. Yeah. So it all depends. It's one voltage minus the other one divided by the impedance. So you can have harmonic here, but they cancel when they get subtracted.
Yeah. Thank you so much for clearing that up for me. Yeah.
The other question. I'm glad that you're asking questions. It means that you're. Next time, just take some books.
Or take the course that you are developing next semester. Is it on machines too or not?
Part of it is machine, yes.
So that is good demo of that one. So you make an advertisement of it. If you want to know more, take the next semester course.
Take my graduate course.
Yeah, that is nice to take that.
Any feedback?
Any more questions?
I have a quick question. So there are also some asynchronous servo motors, right? So why not use them, and why use brushless motor? What type of over asynchronous motors?
So the good thing with this is that they usually have the application. The good thing is that the drivers of this are like very versatile. It's like plug and play. So you can apply the drivers that you have for this BLDC machine applied to another one. So, of course, there are other types of machines that are used, but these are the ones that are the trend.
And also, can you just quickly show the part where you calculate the derivative of the torque? Final equation.
Yeah.
So here, that derivative term, it is kind of discrete, right? Because S is discrete.
Yes, S can be, that's what I'm saying. S is at every switching interval, S can be +1, -1, or 0. When we have PWM, depending on which PWM we have, which phase is connected to positive and which 2 are connected to negative, or which 2 are connected to positive and which one is connected to negative, it's going to be either +1 or -1. And when PWM is up, it's going to be equal to 0. But at every switching interval here, you will have this torque calculation.
Can you design linear controls for this kind of system?
Probably that's going to be another future work that maybe. Yeah, we can brainstorm on this.
How about that constant duty cycle, the simulation? Do they use that in practice or not? Is it?
Yes, because
I see that. Go to your simulation. Is it simulation or practice? Go to the result. One more. Yeah.
Yeah, here, because you want to control the effective voltage that is connected to the machine, applied to the machine, you usually apply PWM.
That's what I'm saying, that with fixed duty.
Yeah.
I see that is 30% repo.
Yeah,
Is
that's
it acceptable?
Yeah, that's why we try to mitigate it. So it is the 180-degree operation. It has high voltage DC utilization, but the drawback is that it has high torque ripple. Because of that, they usually use 120-degree operation.
That's what I was saying.
Yeah, 120-degree operation, it also has its advantages, but it has low DC voltage utilization because for 120-degree, one leg is not connected to DC voltage at all. So you don't use the money you've paid for the DC source. So here, we said, okay, let's try to fix the one that has higher DC voltage utilization.
Okay, nice work, yeah. That is interesting result. More questions? No? Yeah, go ahead.
So, thank you for
Yeah, over time, but if somebody has a class, can leave. But
I can be here.
Yeah, that's what I was saying. You can continue. Yeah, just go there. But if anybody has a class, want to leave, you're welcome to leave. But go ahead. Yeah.
I don't want to become a villain.
No.
Okay, I'll just ask the question.
So when nobody leaves, it's a good sign. They are also interested.
So, can you go to slide, I think 14? Before slide 15, I think it was before slide 15.
Yeah, just because you remember my slide number. When I was presenting my PhD dissertation for my qualification exam, for my very final exam of my PhD, we had a student there who was saying that in your PhD thesis on page 257, you've written this. And I was thinking, how do you even know that it's on page, what has been written? And some people have some very good memory. 14.
So we should remember to treat his dissertation the same way.
So, here you said that you have some magnetic tablet that you take outside the rotor and which emulate the same kind of B or the field flux that the Hall effect sensor can interact with and then track the rotor position. Now, as you started with your slide, the BLDC motors have a range of application. They can be really small, they can be really big. Now, and depending on that, suppose I'm using it for a conveyor belt and I'm using it for a servo motor as well for robotics. And those are very small motors. Now, if I want to implement Hall effect sensor there and to have a tablet there, what is the guarantee that, I don't think I'll be able to guarantee the isolation.
There is no guarantee anyway.
It's so isolation from the tablet, because they are also generating the field and then it's in the different direction, I suppose, then the field has to be there with the stator rotor interaction. And then this is also important for me to detect this field. So in those cases, do you go with the sensorless control? Or
they usually go with sensorless. Instead of Hall sensor, you can also use resolvers or other methods to detect the position of the rotor. That's one cheap way to find the position of the rotor. So the more expensive one use even optical resolvers that they try to detect the position very accurately. So this is in everyday applications. But if that's I understand, because we were doing a project, because these magnetic tablets were not glued correctly, we had a lot of trouble because we had a lot of torque ripple and we had to adjust these magnetic tablets. But yes, there is no guarantee that you can basically do it. Then you have to look for other options, either resolvers or you go brushless control, sensorless control.
Sensorless. Yeah. So Yes, so because I'm like Ninad and everyone else was saying about linear control as well. So I'm used to the induction motor control where you use vector control, and even for the synchronous machines we use vector control and sensorless control. And here you are taking advantage of the basic torque equation itself and the detection of the torque. So in this case, going sensorless because it's solely dependent on the torque. That is, and you're using a lot of estimation method on the basis of measurement. I think is it one of the things that we can improve on because
yeah, potentially yes, that can be improved.
Okay.
Because the thing is, what I've shown here was just the conventional methods, 120 degree and 180 degree. And if you buy a BLDC motor, I would say 90% of the time you'll see that they have 120 degree control logic embedded into their system. But obviously, yes, there are always ways to improve it. What's the other question?
So back to the slide where you were looking at the experimental results, and you were comparing the torque curves. I was curious because I can certainly see that there's a decrease in variance between those two signals. But in terms of things that are going to be say really important, it seems like when you would want this most is when you're doing, like you were describing, fine motions, probably quick switching kind of motions. Did you look at the effect it had sort of finally on position of the motor? Because like, yeah, torque is certainly important, but what you'll end up caring about, the end result of it is really going to be the second derivative of these things. And I can look at them and say, these two things, it looks like an improvement. But did you do any analysis on that second derivative to see, okay, what is that translating to in terms of better exact positioning?
No, we haven't done that.
Okay.
But I get your point that the final thing that matters is the position, the ripples in the position. But I guess when you have lower torque ripple, if you write Newton's second law of motion, so you have lower torque ripple, you will have lower ripples in the position, of course, because it's going to be torque, electromechanical torque minus torque of the machine, torque of the load, divided by moment of inertia multiplied by 1 over s. It's going to be like a.
Oh, sure. I just mean, just from looking at it, I can't tell you how thin those little peaks are.
Yeah, if you look at this, so this is basically, it's not, we cannot compare it with a flat line. You have to compare it with this one.
Yeah.
This one is 0.42 Newton meters is 0.09, or let's say 0.1, almost more than 4 times better.
Mm-hmm.
But again, I get your point, but I guess because you have lower torque ripple, electromechanical torque minus mechanical load torque is going to be equal to 1 over JS. And this speed is going to be that. Then you take the integral of the speed, that's going to be the position.
Mm-hmm.
So it's going to be the integral of it,
yeah,
derivative of it. When you take the integral, these ripples become even smoother.
Okay, yeah, I just couldn't tell that from how zoomed in it was at this point.
Because if you have something like this, you can expect that the ripples in the position will be lower because it's going to be twice integrated.
Mm-hmm.
Does that make sense?
Yeah, I appreciate that.
Any other question?
Final question.
Thanks for the interesting questions.
Okay, so then with that one, thank you again. Okay, good. Okay, have a good day. See you next week.
Doing well.